Yeah, first of all, let me say, really thank you for organizing this workshop. I think you really did a great job in creating a conference feeling as close as it can be a conference feeling when it's only remote. Um, so what I will talk about is mainly about, you see this image here at the center, which where you see a disk, an inner disk that's casting a shadow on an outer disk. And in my talk, I will mainly talk about how this configuration could be established or was established as a consequence of infall. Before I start, to the lower right, you find a QR code. So for those of you who are playing one with a smartphone, feel free to scan it, and there you will get access to a folder where there are some videos. There's a draft of the paper that I mentioned and some other information, including the references that I made in the talk. As an introduction, what's the motivation for the study? So let's go back to the beginning of our workshop when Megan gave a nice review about about star formation, and where she pointed out that stars are not isolated entities, but they are in fact they actually form in filamentary structures, and they are located in different environments, as we also discussed here in this workshop. So there is certainly like an importance there that you have these really different initial conditions. And that's something that's kind of my background, which I've been carrying out MHD zoom-in simulations, looking into filaments and then applying higher resolution to really zoom in onto the formation of individual stars. And that's something I've been doing for a number of objects. And I want to briefly mention this here, since then you also have the option of looking into the magnetic field, something that wasn't really mentioned during this talk, because presumably magnetic fields don't play an important role at later stages, but they certainly are of importance in the very early phase, and this was like the opportunity to bring that up. So based on these simulations, so let's what you see here is a plot of the accretion of the think mass, or like the evolution of stellar mass in a simulation of a giant molecular cloud, and each line corresponds to the accretion profile or the think mass profile of a different star. And what the point I want to make here is, you have even though the stars end up with a very similar final mass, they can actually have very different accretion histories. In some cases you accrete most of the mass, or basically all of the mass, just in 100,000 years. In other cases, you actually have like late accretion events. And these late accretion events, that was something that really triggered my interest, and I was thinking how to model this, and was talking about this with Kees Doelemans when I came to Heidelberg, and he was also very much interested in the infall on late encounter event, but his motivation was more from a different point of view, more from the observational point of view, namely he was in particular thinking of these two objects, HD 100546 and ABO Riga. These are Herbig stars that are presumably a few million years old, and nevertheless, even though they are relatively old, they have these dense structures around them, these envelope tail-like structures on scales of thousands of AU. So what we did was we carried out simulations. What happens if an isolated star, like a single star, just interacts with gas at a later stage? And what we found, indeed, carrying out hydro simulations, we found that you can actually produce these arc structures through such encounter events. And what we also found in a follow-up study then is that this is also a way of actually creating a disk. So we called it second generation disk. So you have an encounter event, the gas is captured, and then you produce you produce a disk. So what we are thinking then is, well, if you can produce a disk in this way, can this maybe also be a mechanism to explain such observations? Namely here, these shadows that are, as we know since the work of Sebastian Marino, that these systems can be explained by a configuration of a misaligned inner and outer disk. And so the main question that we had then is, what can late infall actually cause the misalignment of inner and outer disk? So you form a second generation disk, through infall around an already existing star disk system. That's something we've been trying to do, and I hope the video works. If not, I will stop it. So that's really what we are doing. You see this cloudlet capture simulation. You have a blob of gas that's approaching a star, or from another perspective, if you consider the star is moving, you can also consider it as kind of a flyby of a slow walk-away star. And what we are doing these are repo simulations, purely hydrodynamical. We consider only isothermal gas. And since this is a rather simplified setup, it allows for a nice parameter study. We vary the infalling angle. So we vary it from 0 degree, 35, 60, 90 degrees. We consider various rotation, namely prograde and retrograde. So in such a way that you have the infalling cloudlet along the rotation of the disk, or anti-rotation, or in the opposite direction. And then we apply these parameters here. I won't go into detail about them, but let me just emphasize. So the stellar mass that we assume is 2.5 solar masses, and the infalling mass is about 10 to the minus 4 solar masses. Then you can see here, this is like the visualization of the scenario for 0 degree infall in the retrograde scenario. In the upper panels, you see it on the large scales. So you can nicely see how the cloudlet approaches, and then you end up with this arc or tail structure while the second generation disk falls. Then if you zoom in further, you can actually see the inner disk here as well. And what you see is during the evolution, the inner disk is still there, but it starts to shrink. So its size is reduced. So this is a counter-rotating system, and the inner disk shrinks due to interaction with the outer disk. This becomes particularly clear if you compare it to the prograde infall that is shown here. So in the upper panel, you see prograde infall, where you see the inner disk, the size of the inner disk remains approximately the same, while in the retrograde infall, it changes. And that's consistent with conservation of angular momentum. And to summarize here, retrograde infall causes counter-rotating inner and outer disks. It also creates a larger and deeper gap between the inner and outer disk, which is possibly interesting, also considering transition disks. It causes shrinking of the inner disk, and also you can see it also has an effect on the accretion rate. So in the case of retrograde rotation, you have an enhanced accretion profile, as you can see here in the lower left. So far, so good. So these are only scenarios of 0 degree infall. What about the inclination? So we looked into this as well. The two upper panels are the ones that you show already. The lower rows show the increasing inclination for the retrograde scenario. So you have 35, 60, and 90 degrees. And what you can see is the higher the inclination, what you would expect also from theory, the less is the inner disk affected by the infalling cloudlet. So for 90 degrees infall, so that's the lower panel, you can see that the inner disk still remains quite intact. And that's interesting because this might possibly mean that for higher inclination, so shadows that have a high inclination, if they form for this scenario, are supposed to be longer lived than if you have like very low inclination. One last thing that I want to mention here regarding these simulations is the eccentricity, and I want to mention it because it is potentially interesting for observers. As you can see here in the left panel, you see in the upper panel the eccentricities of the inner disk, and in the lower panels you see the eccentricity of the outer disk. And what we see is that the infall triggers a mild eccentricity in the inner disk, while in the outer disk you see actually significantly larger eccentricities, which is not surprising considering the nature or the formation history of the two disks. And so we haven't looked into this in detail yet, but we speculate that this is actually a feature that one should see in observation. So this might be a nice way to test the scenario. So if you see shadows from outer disk, if they are formed in this way, then we expect like a relatively high eccentricity of the outer disk. And that brings me like to like a disclaimer here as well, because so this was a way of saying you can form these misaligned systems, you can form an outer disk around an inner disk, but what we are not saying is that all shadows are to misaligned infall. In fact, there are a number of cases that have been explained already through other mechanisms, for example, HD10453, and I think there's also a poster here by Rebecca Nealon. There were two nice papers out a couple of weeks ago where they explained the misaligned configuration of that system through a combination of an inner and outer companion. Or there's also work by Chu, who considered an inner perturber, namely a massive planet, that can potentially trigger some misalignment. And there's also maybe the possibility of disk breaking. But the point is nevertheless that there is a zoo of different disks that we know of. So let's not forget about this possibility. And more general, which brings me more back to the beginning of my talk, really the importance of thinking out of the disk. So we know there's more and more evidence observationally that we actually have these streamers that are feeding young disks, or not necessarily disks, of young photostars, as you hear, for example, the one paper by Jaime Pineda, but there are also other papers that show this. And I think it's also for the discussion later on really important to think about the environment threat, maybe also as a support, as it can possibly supply the mass reservoir or also trigger some features in the disk. And I think with that, I'm probably running out of time here. And I'll leave you with my takeaway points, namely that retrograde infall can cause counter-rotating disks that lead to shrinking of the inner disk and the possible formation of gaps and enhanced accretion, as well as we expect the outer disk to have higher eccentricity than the inner disk for infall-induced misaligned systems. Yeah, thank you very much.